Today I'll be talking about high-dimensional black box optimization, but in small data regimes. So I will be discussing problems where we want to try to design something, but we have a small amount of data where we would like to try this design we got in order to achieve the optimum solution. And I titled this towards effective data-driven optimization. The reason why I call it effective is because in many real-world problems we have been focusing on today, it's the flip side of the coin in machine learning. So today in machine learning, you see the big data era, the big neural networks era. In a lot of problems we are facing, it's the other side. We have small data, we don't have big neural networks, and we still would like to resolve those problems and find the optimum. So to start, let me just frame the problem. What we are trying to solve is to maximize a function f of x. So that's the function f of x we would like to maximize with respect to some input x in a domain. Now, there are no restrictions really on the nature of that input x. It could be continuous, it could be discrete, but we have some properties of the function f of x that makes our life hard. The first property is we don't know the analytical form of this function f of x. So contrary to deep networks, for example, we cannot put here a cross entropy loss, or we don't know how that function looks like. And additionally, this function is very expensive to evaluate. So we cannot evaluate as much as we want from that function. We have a budget limit by which we can evaluate that function. And the reason for that is like computational cost or money cost or whatever you have. So as an example of this, consider a molecule design task where you would like to design a certain molecule that achieves certain properties. So the molecule itself is presented by X, which is like a graph representation of the molecule, like a smiley graph, for example. And the black box function F is some property of the molecule. In our case, we consider P log P, which is penalized water octalon level, which is not ideal in general for molecules, but I'll have a word on that later. And then your goal is, you want to try those molecules in order to achieve a high P log P value or a certain property of your molecule. Now, the problem is that one evaluation of your molecule, if you want to do it in the real world, includes wet lab experiment where a chemist, will go and manufacture this and just put it there and then test it and see what happens. Now, of course, we have to be data efficient in this perspective because we cannot allow the chemist to do for me 1 million or 1 billion experiments or something like that. We have to be very data efficient. Additionally, if you think about, maybe a closer problem is hyperparameter tuning in machine learning tasks, you would also see a similar problem. You would set the parameters of your neural network or your algorithm, and then you will take maybe a week to evaluate it, to train it and then evaluate it. And now you want to do a small number of those finite trials in order to maximize your performance on your validation set. So what we have is we have a function that's not known analytically, and we have a function that is expensive to evaluate, and we would like to solve this problem, but we need to be efficient in our solution. Now, we are also going to assume a sequential process, sequential data-driven scenario by which we would like to solve this problem. So we will have our agent, which is the learner, and that learner will emit some X value, so values of a hyperparameter, a molecular structure. Then it will go and get evaluated in the black box, which we call it black box because we don't know it. So it's kind of like a black box for us. For example, a chemist will do a wet lab experiment, or you spend a week training your ImageNet and then get a value. And then after that, the black box will spit out a value f of x for us, which is the value of the black box or the value of the function at data trial x1 that we have made. We collect this data and then we move in rounds, so we move over time. And then we repeat this process, so we collect more and more data. Our goal then is that we would like to improve the guess of the optimum, but being data efficient in how many trials we would like to make. So the number of queries we would like to have to the black box should be reduced. And then we would like to, as we gather more data, to improve our guess of the optimum more and more. Now, a method that does that is typically referred to as Bayesian optimization, which I'm sure a lot of you know about. But at a high level, Bayesian optimization operates in two steps. In the first step, we learn a Bayesian model, and I will say why a Bayesian model. And then the second step maximizes an acquisition that will determine what's your next probe you should try in the real system. So the reason we would like to have a Bayesian model is twofold. First of all, we would like to know those uncertainties about our data. Because the point is that since we don't know anything about the black box function, we have to trade off between exploring and exploiting what we know. So do we explore a new thing or do we exploit a new thing? So now if we have a surrogate of that environment that gives me uncertainty estimates that tell me, okay, look, I'm not sure what's going on there. I am not sure what's going on here, but I'm pretty sure here in this region, I have some good results. Then I can use this information in order to have effective trade-off between exploration and exploitation. And that's the goal of the acquisition function. So the acquisition function takes the model we built, right? So post here, post is the posterior model over the black box function. And then it will try to trade off this nature of exploration versus exploitation. So there are many of those acquisitions. Maybe most famous of them is expected improvement or UCB, upper confidence bounds. But as an example, expected improvement, what it tries to do is it will try to fetch the best point for you, such that on average over your posterior model, you would like to improve the function value over the best you've known so far. So f of x plus is the best I know in my data. F of xj is my prediction about what the function would do in point xj, given my model. And then I try to maximize that. So I try to find an x to try that maximizes or has a high expected potential to improve over the current function value. As a choice of the model, we will also use a Gaussian process. Now, why are we going to use a Gaussian process? Because Gaussian processes are extremely data efficient. So yes, you can, there are techniques that use neural networks. There are techniques that use Bayesian neural networks. There are a lot of techniques out there. But maybe mainstream BO today, maybe I don't think that's a generalization. I think like some of the best BO algorithms out there, they are actually still using Gaussian process. And the reason for that is because we would like to generalize and we would like to learn about uncertainties very effectively from small number of data points. Why? Because that's the goal of BO really. So this is a two-step procedure that we will execute. And then upon minor tweaks in this procedure, so if we are doing models correctly, so for example, if we think about the noisy processes we want to embed in our model, and we think about the right acquisition to use, you can actually get state-of-the-art low-dimensional results. And this is the NeurIPS competition that Vahid was mentioning before. So there we had a hyperparameter tuning task and consisting of up to hundreds of parameters we would like to tune. And then the goal was, to try to solve this problem as effectively, efficiently as possible. And this was a competition organized by Twitter, Facebook, and VeloHigh and 4Paradigm. And it was a relatively large competition. And we were able to win that competition by maybe making two tweaks to this framework I described here, whereby we were smart about the choice of likelihoods we would like to have. So we didn't assume Gaussian likelihoods, we assumed non-Gaussian likelihoods. And also, we didn't choose one acquisition, we chose a multi-objective acquisition because we realized that different objectives give us conflicting results. And then here is a comparison. So we created an algorithm called HIBO. And so HIBO corresponds to heteroscedastic evolutionary Bayesian optimization. Heteroscedasticity comes from the reason that we don't assume Gaussian likelihoods. Evolutionary, because we use an evolutionary algorithm to solve the multi-optimization objective. And then we compare against a lot of other techniques out there, including Turbo, HyperOp, BOHP, random search, Nevergrad, OptiTuner, and many others. So we are in blue, and you see we do much better than those other algorithms. I think something which we found really very interesting here is that BOHP tends to really underperform those tasks, and it actually tends to perform relatively very close to random search. This has been confirmed by other people as well. So it's not only us observing this behavior. And we think because the BO component in BOHP is not the state of the art. I think if we would change that a little bit, we should get better results than this. But out-of-the-box BOHP doesn't seem to do well on those specific base-mark tasks. So anyways, I don't want to dwell on this because the talk is about high-dimensional BO. So I just wanted to mention this by passing. And now let's switch our attention into scaling a high-dimensional BO beyond scaling Bayesian optimization beyond those low-dimensional domains. So far, I have described for you the process that's on the left, right? So I told you, okay, we have a space X. We build a surrogate model, which is a GP. This is the Bayesian model we have. Then we maximize the form of an acquisition. We chose it to be a multi-objective. It could be something else. Then you maximize the acquisition so you get a new query point. You try the query point, and then you repeat. So effectively, this BO loop is building a map from the search space and back to the search space. So you take X, you build a map, go back to X. Now, when it comes to high DBO, the idea is really simple, and it almost always involves a dimensionality reduction step. So the red lines I depict here are kind of additions that you would do to standard Bayesian optimization, where now from X, you go to a lower dimensional space Z, and then you execute BO in that lower dimensional space Z. So effectively, this is the latent space, typically lower dimensional and continuous. And then you go into this lower dimensional domain, you do Bayesian optimization in this low dimensional domain. So you fit a GP, you maximize the acquisition, you get a new Z, then you go back to your original space, and this process repeats. Now, in fact, it's the way by which we construct this embedding or this projection that differentiates algorithms out there for high dimensional Bayesian optimization. So there are a lot of techniques that assume linear projections. So they assume that to go from X to Z, there's some matrix A that reduces dimensionality. And this has been there for a long time, and still there's interest in it. Like in 2020, we had a paper on this. 2016 was a very nice paper on this. And those techniques tend to have very nice theoretical properties as well, because the analysis of the problem does not involve big neural networks, and therefore it's easier to understand. Now, though successful, when it comes to really big problems like molecule design material design or things like that, we would really need to go beyond these linear projections into nonlinear projections. And there are tons of algorithms in that field as well. So one of them, for example, is Marconi, which is by also by Mark Dysenroth. They work typically with GP, so they assume GP decoders and so on. But there's a thread of work that is using variational autoencoders as this projection mechanism, and that will be our focus. So we will be focusing on those techniques that use variational autoencoders, which are nonlinear projections. We can think about the nonlinear stochastic projections, really, that will allow us to reduce the dimensionality of the space, then do BO, and then go back through the decoder to the original space. So in short, that's how the BO with VAEs look like, really. So here you have an input space, which I am calling X. So you have X1, X2, up to Xn. So those are n data points in your input space, right? And f of X are the corresponding evaluations of those inputs that you are given. So for example, you have a molecule, which is X, you evaluate it, you got the log P value, then you get f of X. Then the first thing you do with this VAE-based BO, you simply just learn a projection to a latent space Z, right?
Yeah, so Haitham, may I ask you a question here?
Yeah, go on, yeah, of course.
Yeah, so first, when you project to a smaller dimension, it's like one way to go theoretically that, yeah, you can go to a smaller dimension, it's unique, but when you want to come back and recover that, well, there are many solutions. I know that for variational autoencoders, you have a generator, so you get a sample from it based on some distributional assumptions. So the problem doesn't really exist if you have multiple samples of them so that you explore their space based on your distributional assumption. Now, don't you think that this way somehow the efficiency is touched because you want to generate actually less points as possible, and then going back to X is actually not that much easy?
Right, yeah. So, well, okay, that's a good point. So in fact, this is the topic of this slideshow. So
All right.
Okay, what you touched on is exactly this problem, which I write here. So when we do what I am saying, right, we don't anymore solve the exact objective. We solve a surrogate problem. And in that surrogate problem, we're not looking for one point, but we're looking for distribution over inputs that is actually going to be successful. And now the question is, how can we make that efficient, right? So yes, I will come to that. This is the
So
this
you
is
see also the x to be continuous is a restriction in this method, or a combination?
no, no. So in our experiments, as I will show later, we have worked with smiles, which are discrete grammars of molecules, right? So, and we also worked with arithmetic generation, which is like a binary matrix, right? We did work with images, which are grayscale, right? So that's continuous. But the point is that what I find interesting is that I think there's a trend today where we try to solve large discrete problems by mapping them into a lower dimensional stochastic place. And I think this fits within that setting, that framework. And in fact, I will show under what theoretical assumptions you would need in order to guarantee that you still recover the optimum in the original space, right? So yeah, so all great points. I think I'm coming to them. If not, please stop me and then ask me again, then we can have a discussion. Yeah.
Thank you very much. Please.
Cool. Right. So simply this VAE thing, right? So we have those x's, and then from those x's we construct this latent space, which is made of z and f of x. So z is the encoded input, and f of x is the black box value we had for the original point x1. So we don't necessarily need to map f of x because it's just a label. And for that input x1, we had label f of x1. So what we do is we give for the encoded one, f of x1 as well. Now, with this available, now we do BO in the latent space. But now just one tweak we need, just to be clear on this. The variational autoencoder will give me a distribution in the latent space, right? So instead of giving me deterministic point, it'll give me a Gaussian distribution typically that I would need to sample from it those z's. So now you are dealing with an input in the latent space when you want to fit the GP, right? You are dealing with an input which is stochastic, so it has uncertainty to it. So rather than using standard Gaussian models, Gaussian process models, people typically use Gaussian process latent variable models, which are better suited to deal with this type of uncertainty. Now, that being said, you can also just take the mean and then feed it, and people do that as well. And then the horizontal line here, all it's trying to do is just trying to do BO in this latent space. So you fit the surrogate, you do the acquisition maximization. Then you get a new probe to try. Once you get a new probe to try, you use the decoder, as Vahid was saying, so the generator. And then that gives me a distribution in my input space, right? So that corresponds to what the model believes in the latent space is a good thing to explore. And then we sample from this distribution, we evaluate the black box, and this process repeats. So more formally, what is happening is the following. So we have two loops. One loop is the Bayesian optimization loop. So this is the loop that you see horizontally here. And then there is the output loop, which is updating our VAE. So we're going to update our VAE, do BO, gather data, update VAE, do BO, gather data, and repeat this process over and over again. Now, of course, we typically schedule when we want to update our VAE, because if we don't, then you will end up with tracking non-stationary target, and that's really hard. So what people do is they assume a budget on your updates, and then they just update every Q steps or something like that. Now, the Bayesian optimization loop in purple here is just standard Bayesian optimization, as you see, GP fitting, maximization of acquisition. But now, when you want to evaluate, we cannot just evaluate the Z value because the black box is defined in X. So what we do is we just map it back to the original space, and then we do the evaluation, and then we repeat. Now, so back to the hit point, please notice that what we solve here is not the problem of X, right? We don't maximize f of X anymore. What we do, in fact, is we try to maximize over latent Z such that if you sample from the distribution of the decoder, you will maximize your black box. So in fact, what we try to do is we try to maximize over all Z in the domain of Z, the average performance of regenerated inputs of the black box f of X. Now, of course, this is a maybe a more general setting than the original problem, because you can easily recover the original solution if your G was a Dirac function, right? So if it was a Dirac distribution, then you would actually recover the optimum, the exact optimum. But what this really searches for is more of a distribution in the latent space, conditioned on some optimum latent space, such that expected function value improves. Okay. So I talked a lot about those latent spaces, but I think it's relatively, I think it is well understood in LSBO, latent space Bayesian optimization, that there are properties of this latent space we would like to have for this method to work. So I try to summarize those properties here by calling them property 1 and property 2. What we really need from those latent spaces is we need them to be able to do things beyond just reconstruction. So if we just wanted those latent spaces to reconstruct, then you would train a standard VAE and then you would go forward with that. But please remember that our goal of constructing this VAE is not just to generate inputs, but we need something that's amendable to exploration and optimization in that space, right? Because at the end, I'm going to run BO in that space, meaning that I will need to explore that space. I would need to fit a GP in that space and so on. So this latent space should have knowledge or should exhibit some form of knowledge about the information between Z, which is the latent point, and the function value f of x. So in other words, I want those latent spaces to be discriminative with respect to my black box function. If I have that, then my job is a little bit easier when I explore that latent space, because changes in the latent space are reflective of changes in the black box. So if I optimize in the latent space, I should be able to efficiently try to efficiently solve the problem. Now, the second property is, please keep in mind that the downstream task when we are training a VAE is a GP regression problem, right? Because at the end, as we said, we're going to do BO and we're going to fit a GP LVM. So this second property is we would like that when we organize this space to have some inductive bias in it, such that it takes into account that, or it knows, oh, look, a GP is going to come later. So let me make the GP life easier, or try to make the GP life easier. Now, you might argue, why don't you encode that in the model itself, in the GP model? You can definitely do that. But the point is that here, you have access to a neural network, right? So if you can make it do things for you, you can get very flexible behavior, and maybe you can get better results. And I will show you that we do get better results. So in order to solve the first property, what people have done, so TRIP in 2020, they have simply introduced a very nice idea, and it's really simple. The idea was, let's take the VAE, and now let's weight the reconstruction error of the VAE by some weights that are dependent on the function value. So if my goal is to maximize the function value, the higher the weights, the more focused the elbow will be on the reconstruction of those corresponding points. And those points are important because at the end, you would like to maximize your black box. So now you focus on them in order to get a space that can recover those really well, because we think that the optimum will be nearby. Now, the second property has not been studied before, really. And this is the thing we kind of submitted to NeurIPS this year, where we tried to combine what I'm talking about and deep metric learning into one framework. And those are the guys who actually created this work. I'm just the guy speaking. But Antoine, Alexander, Rasul, Ryan, and Ali, those are the guys who really did this work. And then you can read about the work in the paper. And also our code is open source, so you can also download it to play with it. So what I want to say now is, how am I going to induce a bias or induce some inductive notion in my latent space that a GP is coming later, right? So a GP is coming later, and now I want to make the GP life easier. So what do I mean by making the GP life easier? Let's go to Rasmussen's book, which is the Gaussian Process Bible. And this is a snippet from, I think, chapter 7. I read it so many times, I almost memorized this book. So I think this is chapter 7. And what I think they say here, which is really interesting, is that they say that supervised learning algorithms are based on the idea that similar input patterns will typically give rise to similar output patterns. So if you have x1 and x2 close to each other, then x1 and x2, then f of x1, f of x2 should be close to each other. So can we do something? Can we actually encourage such a property in our latent space? Can we maybe make this happen? And now, as I said, there are two directions to do that. You can either go doing it in the GP model, and there's a lot of nice work on that, and Mark van der Wilk has a very nice paper on that as well about learning invariances. But we decided to go the other direction, where we decided, okay, we're going to change the elbow of the VAE such that I induce this property when I am trying to construct my latent space or when I'm trying to fit the VAE. Now, the reason why we did that is because we believe this is more flexible in terms of what warps we want to learn than putting those warps and constraining them within the marginal likelihood of the GP. And we compared against warp GPs, as I will show you later, and it does do better than that. So therefore, we're going to focus on that. And now, me saying whatever I said, I think anybody who knows deep metric learning realizes that those two problems are very close, right? We understand that deep metric learning, for example, in computer vision, it will say, okay, if I have a dog and a rotated dog, right, then I would like those to have similar latent codes because the classifier thinks it's still a dog, right? So now what I'm trying to say is something really analogous from a perspective. It's saying if 2 points have similar black box function values, right, then I want the latent codes to be close to each other. If I have that, then I will meet this criteria that Carl was talking about in his book. So here I try to pictorially illustrate that. I show you here x-axis and y-axis. So those are different input probes. And you have f of x1. And, oh, sorry, this should be f of x2. This should be f of x3. They should be flipped. Sorry for the typo. And then this is the latent space. So what we really want, even though x1 is close to x2 in distance, right? It doesn't really matter much if they get encoded to a similar place. What matters is if their difference in function value is close or not. So because x1 and x3 are close in function value, we would really like those to be mapped close to each other. While x2, even though it was close to the x1 in distance, but the function value is very different, we would like it to be far away or separated by some margin. So in other words, if we have this, then we would have closed latent codes having closed function values, which is in accordance of this inductive bias that is in that book. Yes, Vahid.
Yeah, so I just wanted to mention that one of the reasons that we want to like these two functions to be close to each other into the input space and output space, because somehow inherently we consider that most of the functions we deal with are Lipschitz. And this property is coming from the theoretical like proofs that perhaps we can pursue later. And violating it, somehow it makes it more difficult for us to go through the mathematical foundation and proving things. I just want to, you point out, if we break this Lipschitz condition that we most of the case assume, can we still go through some theoretical properties when we're going and projecting in this fashion?
Yeah, that's great. So in our proof, we actually made Lipschitz assumptions about the black box, right? So we do need those. However, that being said, there is a trend of work happening where they try to use GPs for non-Lipschitz continuous functions, right? That relates a lot to warping methods that people are developing, like was it input warping or output warping? And it relates a lot to criteria of non-stationarity of kernels, right? But by no means, I believe, that field is well developed, right? So what currently works well is when you have a relatively well-behaving function. Now, if you end up with really messed up functions which are very chaotic, right? There are solutions to that. For example, deep Gaussian processes are an option to go there, right? But they are still very hard to do inference on. So if you have a function that, say, it looks like a sigmoid or something, right? Yeah, you can still do fine with a standard GP, but to really fit that, you would need something much more complicated. So therefore, there are two broad directions, I would say. So deep GPs is one going in that direction, I would say. The other one is things like deep kernel machines or deep kernel type of methods where they try to learn very complicated kernels, right? So I think we might get to solutions of those, but I would say it's a bit early in that to try to get them to the real world. I think they need a couple of years of research then they will be where this technique is today.
Thank you.
Yeah, no problem. Yeah. So effectively what I was just trying to say is that I was trying to say, okay, if for example, I have xi and xj are close to each other, then I want their latent codes to be close. And therefore I can penalize based on the distance in the z value. So if the z value is very close and the function values were close, I don't get penalized, which is good. But now if the z values are far and the function values are close, I will get penalized. And vice versa. So in the case my function values were far and the z values were, what I need then is that the z value should be separated by some margin. And therefore we can define this type of loss, where now this will only get activated if the z value are close, because the norm will be close. If that's the case, then you will get a positive loss here, and then you will discourage that behavior. So yeah, go on, yeah.
A question here. So by distance between,
yeah,
what measure of distance do you use for the latent space?
Oh, so for now we have been using L2 norms, right? For the latent space. I think there is a member of the team that started working on more like Riemannian geometry kind of distances, but we are stuck because they're very hard to compute. Yeah.
And the question is that here, for each x, we have a distribution in the latent space rather than a point.
Yeah.
So
yeah, this should hold on average. Yeah, this should hold on average.
Uh-huh.
Yeah.
I see. Okay.
Cool. Okay, and then yeah, so here I just pictorially depicted for you, right? So I pictorially depicted. So I just show you on the x-axis z distances, on the y-axis function values, and then I just would like you to see that, okay, if my z distance is far away, so on the x-axis we are at 1, right? But my function value is low, then I will get penalized. So red means I'm being penalized. Now, this is good, but we would like actually to have more of a gradual penalization. So the more we get closer in function values, and the more you make a mistake, I want you to be punished more. So that's why we just create a smoothing mechanism without going into the math. I think you can read the equations in the paper. That there isn't much intuition to give here really. It's just that the idea we wanted that the closer you get in x, the closer you get in f of x, you get penalized more than if you don't get close. So that's why here, this is the smoothing result. What you see is that if you are making a mistake at 1, and your function value is almost near 0, the difference of function value is almost near 0, you get more penalized than none. Now, this is based on 2 points. We can generalize that to triplets. And now in triplets, so what I talked about is very similar to contrastive deep metric learning. Now we can also look into triplet losses in deep metric learning, and we try to carry them. And here the idea is very similar, but now it's actually based on 3 points, not 2 points anymore, because it kind of takes into account a relative distance measure. And again, without diving into all the details of the mathematics, you can see similar behavior here, where again, the smooth version, if we are high in distance but very low in function value, we get hurt more than if not. Okay, so now this, if we incorporate this loss inside our VAE, then we should structure the VAE as latent space in a way we would like it to be, such that 2 latent codes are close if the corresponding black box is close, and 2 latent codes are far if the corresponding black boxes are far, which is, again, according to this induction principles that we had when we were doing supervised learning for well-behaving Lipschitz functions. Yeah. Now, all is good, right? But at this stage, you should be worried, right? Because the point is that you should really be worried because I told you about data efficiency, like the title of the talk is about data efficiency. But in both solutions I proposed, or one by Trippe and one by us, right? We always required access to the black box, right? So for example, for Trippe, we required those weights to be proportional to the black box function value. So we need access to the black box function value. And in our case, we needed to categorize data based on distances of black box function value, meaning that we also need access to the black box function value. But now I promised we should get something sample efficient. And what I mean by sample efficient is how many black box function values you would like, because that's the problem with BO. So now you clearly see that this goes against what BO tries to achieve, because now to structure those latent spaces, you would like to have a lot of function values. And we don't want that. So we want to get rid of that. So here you can go two directions. Maybe the most prominent direction that been used a lot in today's world is the idea of self-supervised learning. Now, when it comes to our world of BO, it's really hard to carry the concept of self-supervised learning, or specifically, let's say one concept of self-supervised learning, which is this data augmentation. Now, the reason for that is because although we don't assume labels when we augment data in computer vision, for example, we implicitly make the assumption. Because we say that, okay, I'm going to rotate a dog, it's still a dog. I'm going to crop a cat, it's still a cat, etc. So we made those presuppositions about how we would like to augment our data. When it comes to augmentation in black box optimization, this is a much harder problem from the following perspective. If you have a molecule that gives you very healthy behavior, if you take one atom and put it down, that molecule can go from being an excellent molecule for you to a molecule that can kill you. So what sorts of augmentation we would like to do is very unclear to us at this stage if we don't have knowledge of the black box function value. Now, learning inverse models can be interesting. This is something we are looking into, but we really think this is a very nice direction for future work. And we don't know how to solve it yet. So if anybody interested in something like that, please talk to me. We can try to see if we can collaborate. Now, what we did, however, is we went completely unsupervised on the problem. Now, this is in accordance of the philosophy of the, for example, Yann LeCun as well, that believes that, you know, a lot of animals and humans learn by unsupervised learning. And what we're going to do is we're going to leverage the power of unsupervised learning. So you give me a set of molecules that are valid molecules according to their smiles. What I'm going to do is I'm going to just bootstrap initially a feature representation that can reconstruct. And then I'm going to fine tune this representation with metric learning and other components as I do my BO. So therefore now I'm going to just bootstrap a good initial set of features. I'm going to then improve it as I go in order to get better features that are discriminating with respect to the black box function. So what we have is the following. So we have three components to our elbow. The first component is the standard unsupervised learning component. The second component is the following. So we have a component that relates to the metric loss, which I talked to you about before. And we have a component that tries to regenerate the labeled inputs and also has a K-alter. Now, those weights you see here, those are the weights I was talking about, right? And those are the weights that correspond to the function values, or need access to the function values. But now we are in the world of a semi-supervised setting, whereby we assume so many unlabeled components M and so less labeled components N. So therefore, we have N is much less than M. And now to fine tune, we're just going to need those M from the BO loop, which is much less than the N plus M data set. Now, this leads us to the following algorithm. Now, please notice, right, that this algorithm is very simple to implement because it's the same as latent space BO with just one difference. And that difference is just corresponding to which retraining you would like to do, right? So here we have additional components to the elbow, which is in accordance to what I said before, that we would like to change the elbow equation in order to encourage what we would like to see. And then we fit the VAE, we do latent space BO, and then we repeat this process over and over again. So at this stage, you might really wonder, okay, cool result, but can this converge? Can this method converge? Okay, so what we did is we studied the regret of our algorithm, right? So we studied the regret of our algorithm And for those of you who know, regret is kind of like a measure of how bad you are doing. And so it's like the distance from what we have thinking and what the real optimum is. And that's what you see inside this inner part here. So here, this summation over K, that's just the summation over the Bayesian optimization steps. F of X star is the true optimum in the original space. And this part here is our belief over what the function is from our algorithm. So this inner part is a standard, really. There's nothing fancy about the inner part. This is just the standard BO. The outer part, on the other hand, is the retraining steps of VAEs. So the outer part takes into account how will this inner part solution get affected as we change the VAE over iterations. And then we are able to show the following theorem. So we prove in our paper that we can actually get sublinear regrets asymptotically with high probability. So the average regret of this form, as the budget goes to infinity, it will go to 0. And that happens with a probability of 1 minus delta for some small delta. Now, this is not magic. There is something I don't like about this theorem, and that's an assumption we make. So in order to prove this, we needed to understand the effect of this outer iteration, what it's doing, right? Now, this is a very hard problem because, this is a neural network. It's changing over time. The feasibility set of the inside BO loop is changing with respect to the outer loop. So what we did is we made an assumption that we think is realistic, but we might argue otherwise, and that's fine. The assumption says that at certain iteration L, right? So as L grows, this L outer loop, at a certain iteration L, the probability that you can sample X star from the decoder increases. So we assume that there is an improvement of the recovery property of the input domain of the VAE as data comes in, or as we do weighted retraining. Now, that assumption is less restrictive than assuming that at every iteration, we would like to have access to the, we would like to assume that the VAE reconstructs for you, has the capability to reconstruct X star for you. But it's still an assumption. So we assume that this probability increases, and that's something that's worth digging into and trying to improve. We were thinking that maybe we can get a pack bound for VAEs because this relates to the generalization property of the VAE, really. Trying to understand at which stage the VAE can recover the whole domain, the whole input domain. And that's something we're digging into. So this is an assumption we'd like to get rid of, but we just don't know how yet. So if you have any interest in this, please let me know, and then we can try to see how we can work together on that. So again, this assumption is new. It's not common to BO, and it's less restrictive than assuming you would recover the property of, you would be able to sample X star at any L loop, but it's still an assumption which hopefully we can remedy in the future. Now, with that being said, we did an analysis of this assumption in our paper, and we showed necessary and sufficient conditions in order to guarantee convergence. And we know that this assumption is not necessary to guarantee convergence. There's something weaker that we could do to guarantee convergence. But yeah, this is early study, to be honest. As far as I know, this is the first regret proof of latent space Bayesian optimization convergence. So although we don't like this assumption, but it's worth at least putting this work out, so maybe somebody could improve it. Right, so now let's jump to experiments. In experiments, we considered the following 3 scenarios. So the first scenario is we had a topology domain. So this was a domain where, starting from a blank image, you would like to recover some mechanical structure. So the mechanical structure looked something like this here, and then you would run BO in order to get that mechanical structure. Our input X was a 40 by 40 image, which is like a 1,600 dimensional vector. Our function f of X was the distance to the structure we would like to construct, and our Z latent space was 20 dimensions. In the second experiment, we worked with arithmetic expressions. Here, you would like to generate an equation. Now, to represent this equation, there's a formal grammar that represents this equation. And therefore, x here becomes 180 dimensional values. And now your function f of x is the distance to that equation, and z is 25 dimensions. And maybe the most exciting setting is this molecule generation setting. So here we have smile graphs, which are representative of molecules. So now we search over the space of molecules, or smile graphs. The property is called penalized log P, which is given to us from a simulator. And latent space was 56 dimensional. We wanted to answer the following three questions. The first question, we wanted to understand if this metric learning actually helps GPs. So can GPs generalize better by the usage of metric learning? And if they can generalize better by the usage of metric learning, then that means that metric learning has actually given us some nice discriminating features with respect to the black box, which was our goal to start with. And then if that happens, does that improve BO when we have a lot of data? So when we have a lot of labels, does that improve BO? And if it does, then what about when we cut the labels? Do we still get any improvements? So to start, I would like to show you here some of the results of the structure of the latent space and the generalization power of the GP when we use the metric learning. So those are 4 graphs. Every 2 correspond to a task. So the first 2 correspond to expression. The second 2 correspond to molecules. What we measure in the latent space is we take our data, we cut it into good points and bad points. And then what we would like to see is that the distance between good points get together, the distance between bad points get together, and the distance between good and bad points go far away. Because if we have that, then we know that the space got structured in a way we would like it to be. On this first side, that's like standard VAE structure. And on this, on the second, like 1, 2 in figure 2, that's what we see after we apply metric learning. So again, you could see that the high score points get close to each other, low score points get close to each other, but now the distribution of distance between high and low score is a little bit far away. And that's similarly with respect to the molecules. Now, that being said, the question is, does this structure help Gaussian process prediction, right? So because that's what we, at the end, we will use. So to do that, we ran an experiment where we used our different types of VAEs on different tasks. And then we fit a GP in the latent space. Then we have a held out data set. And then we measure the prediction. So if now the log marginal, the predictive log marginal is higher, then we actually, we actually did better generalization than the other one. And this is actually true. So you see that the contrastive and triplet, both on molecules and expression, they tend to perform well, while on the topology, they do perform better than Belinda, but VAEs with target prediction that try to also predict the f of x value on the input, they do better, all right? So now we know that this is true, so it happens, it performs well. So now the question is, do those actually help the performance of Bayesian optimization in the latent space? So here, we show the function value curves for all of these different tasks, those 3 tasks we considered. And we have some baselines that we compare against. Now, the most important, for me, the most important baseline was random search, because a lot of algorithms claim they are better than random search, but they're not. So that's why we included random search. Now, LBO is latent space BO without metric learning. Now, WLBO is input warping with latent space BO. Because you could argue, as I said, that we should induce this structure inside our GP model. One way to do that is to think about the non-stationarities of your latent space, and therefore add a warping function, and that's what we did. So the warping function we used was a Kumaraswamy warping function, which is also in PyTorch. And then our method is called CLBO and TLBO. So we call it contrastive BO and triplet BO. And then what you see is that, yeah, we do better on the topology and the expression task. And we also do better on the molecule task, but a tiny better compared to a target prediction VAE. So target prediction VAE is a VAE which on the input tries to reconstruct X, but also f of X. So we see in this domain, when we have access to all the data, the us and the target prediction VAE on molecule do similar, although in 1% we're better, but that's just minor. It's not worth even discussing. Now, okay, all that's good, but please notice that in this experiment, for the molecules, we have actually used 250,000 data points. Yes, sorry.
So, Haitham, I want to control time so that we leave some time for the questions for people who might have some questions. I wonder that if you can wrap up in a few minutes.
2-3 minutes I need, yeah. This is, the next slide is last slide, yeah.
Good.
Cool, all right. So just to note here that these successes happened when we have used all the data that is available, so all the labels. So in molecules, for example, we have assumed access to 250,000, right, labels of the molecules. Now, as we said, this is not realistic. We would like to drive that down, so we developed this semi-supervised technique, etc. So now once we go to the semi-supervised setting, we actually see something really interesting, I believe. So let's look at the molecule. So expression and topology, we do better, but I think molecule is much more interesting than the topology and the expression. So when we go to the molecule generation, in this experiment, we only used 1% of the labels. So we took this 250,000 data, and we just removed the labels. We only kept 1% of them. And then what we will see here is that we can still recover state-of-the-art results. So this is orange. This is the orange line we have here. And then we can still see that we recover these state-of-the-art results, but by using just 2,437 function evaluations, as opposed to what has happened previously, which was 250,000 evaluations. And it's also worth noting that SMILE VAE, another technique, uses 2,500 labels, but actually gets a result which is much lower in log P than what we have.
Excuse me, what are the axes on the graphs?
Oh, the axis, okay, so the x-axis is how many function evaluations we would do, so how many calls we would have to the log P function or simulator. And the y-axis is the function value. So our goal is to maximize log P, and for example, which is a property, right? And then you would see that the higher the better. And therefore, yeah, now for expression, the difference is that the y-axis will be like the distance to your sine equation or whatever it is. Cool. So now, yeah, just to wrap up, in the future, what we would like to do is, as I said before, improve this assumption. But also one thing I don't like about those molecules experiments, and I think anybody who knows chemistry will look into this molecule that we created and a lot of other people created and be like, you are crazy. The point is that log P can be maximized, it turns out, by putting a chains of carbon next to each other. So for example, you see this, this chain here gets a log P of 29.14, which is a very long chain that gets a very good log P. But for a chemist to synthesize those are not really useful molecules because they're very long chains. So we would like to, you know, like limit how many hydrocarbons you would like, or carbon chains you would like to have. So what we're now doing is we're trying to improve that, but by using a different notion than log P and working on a much more realistic problem than the zinc data set. So zinc data set is a well-known real-world data set, etc. But now we are trying to work with this COVID moonshot project, which is a project that is trying to get antiviral pills for COVID. And there we need to maximize a property called IC50. Now, what's cool about this is that if the chemist on the website looks at your submitted molecule and they think it's good, they will actually go and put it, implement it, and then test your IC50 and then return a number for you. Now, that setting is very ideal for our problem, we believe, because there has been 18,000 molecules submitted to the COVID moonshot project. Only, I think, about 1,800 or 1,500, sorry, the exact number slipped my mind, but a very small portion of those molecules have actually been synthesized. So now we have a lot of unlabeled data, right? And we have a teeny tiny amount of labeled data. Can our method help there? So that's the next thing we are working on. So yes, so not to leave time for some questions, I end here, and thank you for your time and listening to me.